right. So lab 5 is due this Saturday. Yeah, same with readings for the week. We also have not on here the final project proposal is due this Saturday. Any questions on the style transfer lab due this Saturday? Okay. Well, yes. Well, so there was a lab review for the style transfer lab last week, and there will be another one this week. So Matthew's being generous with his time, and yeah, that will be in at what time, what place?
So the room is scheduled from 4 to 5, 11:70 p.m. CB in the conference building. But last time it took about 2 hours, so if no one kicks us out, probably 2 hours.
Okay, so 4 to 5 or 6 p.m. in 11:70 p.m. CB. Okay. Yeah, question.
We will make an attempt.
We will make an attempt, Matthew says. All right. You'll be guaranteed to hear it if you're there in person. Yeah, question.
What day is it? You said that?
Today. Yeah, day 4 to 6 p.m. Yeah.
Yes.
Yeah, we will do our best. Okay. And understand the situation. Hopefully you have enough information to do the lab based on lectures and the lab spec. We really tried to make that standalone. Usually the class doesn't have these TA review sessions. And so hopefully there's enough for you to go off of on the lab. Without that, yeah, if you have any personal questions as you're going through the lab, feel free to come into TA office hours, my own office hours, and you can get help there as well. Yeah, question. Then the review today will be for lab 5. Yeah.
Also,
so it sounds like this time isn't the best for some people. So Matthew posted a poll about other possible times, so you can feel free to fill that out, and we'll see if we can get a room at the most popular time. Okay, last time we talked about regularization, L1 and L2, and elastic net regularization. We also talked about dropout and its variance. There was some confusion on that one diagram where we showed the 2D diamond and the contour curve of the loss surface. So I made a little demo in 3D that hopefully will clear things up. It might just make things more confusing, but it will be here for what it's worth. While that's pulling up, okay, yeah. Can you see if on the recording is my screen?
That is your screen.
Okay. So here we have the 3D visualization of that same diagram. So what are we looking at here? We have 2 loss surfaces. The one to the right is the true loss function. For example, cross entropy loss. And you can see that its minimum will be at the center of that parabola. And it occurs at x equals 1, y equals 2. And those represent the parameters that you would find if you were minimizing just the cross entropy loss function. And that's represented by this function, which is a parabola centered at x equals 1, y equals 2. Now, this other parabola centered at the origin represents the L2 loss, which is the mean squared, the sum of the squares of your weights. So that's penalizing the magnitude of your weights. And then your summed error is represented by this formula, z equals 1 times the L2 regularization plus 0.5 times the normal loss function. So it's just a weighted sum of those 2 loss functions, and it forms this third parabola. And you can see that this third parabola is minimized at a point that is neither the minimum of one parabola or the other. And so you can see that when we have our loss function is the sum of these two terms, the minimum of that function occurs at a place that is not that is not the minimum of the other two functions. We can turn off the others to see how that is. And in fact, the minimum of this function, we talked about the minimum occurring at the intersection of the goals. This is what we mean by that. So these goals intersect right here. And you can see, and actually, I'm not. Yeah, actually, we won't talk about the intersection of goals. I don't want to further confuse things. Okay, so then that is L2 regularization. L1 regularization. The regularization penalty is represented by an inverted pyramid rather than a parabola. And when we sum that with the original loss function, we get this curve right here. And you can notice that as we navigate around this curve, it still has a parabola-like contour. However, it has this this edge, you might call it, along x equals 0. You see that kind of the edge on the bottom of this parabola. And so you can see that if we're trying to minimize this function, the minimum will occur at about y equals 1, x equals 0. So that's an example of how adding that L1 penalty can cause one or more of our weights to go to 0. Does that help at all in the 3D visualization of those losses? Okay. Any questions on that? All right. And then can you see the PowerPoint on the great, thanks. Okay, so quick quiz. As we increase regularization, this is a question about the bias variance trade-off. The question is, what does regularization do? Does it reduce the error due to bias of model predictions and increase error due to variance of model predictions? Or does it reduce bias and reduce variance, increase bias, reduce variance, or increase bias and increase variance? Try to answer that. Okay, anyone want to take a shot? Yeah. What's your question? It is basically the amount that you're off in your training predictions. Or the error in your training predictions. Do you think you're saying that it decreases both bias and variance? Not quite. So the true answer is that it increases bias and it reduces variance. So when we're talking about the bias variance trade-off, we're talking about generalization from training data to test data. And so your test error is composed of three parts. Irreducible error, which is error that you can't get rid of. That's just due to noise in your test data. Then there is there's error due to bias, which is error due to basically underfitting, and variance, which is error due to overfitting to your training set. And so regularization reduces overfitting to our training set, so it reduces variance, but it increases bias because we are not fitting our training data as close. So another quick quiz question. Dropout is equivalent to which of the following? I don't remember. L2, yes, dropout is equivalent to L2 regularization. And then shakeout. Remember, that's where we sometimes invert the sign of an activation. What is that equivalent to? L1 and L2 OS regularization. That is correct. Okay, so today we're talking about recurrent networks, the vanishing gradient problem, and we probably won't get to LSTMs and GRUs. So recurrent neural networks. So in the past, we have been dealing with inputs that are a fixed size and designing functions on those. Now we're going to try to design a neural network that can operate on an input of variable length. Now, if you were to do that without me telling you how recurrent neural networks work, how might you do that? This is a creative thinking exercise. How might you make a neural network that can operate on input data that can vary in length? So, for example, I'll give you an example. A sentence is not always going to be a certain number of letters long, or an audio stream, like if we're doing speech recognition, is not always going to have a fixed length. So how might you design something to operate on that? Yeah, what do you think? Yeah, totally. So he said if you have a string or something, you can use a hash of that string. Totally. Yeah, you have to design the hash function carefully, because in this case, you would probably want, if you wanted your network to be predictive, instead of a hash function having a random output, you would want to have a hash function that causes collisions, right, between things that are similar, right? But yeah, that's a great idea. And in fact, you can think of recurrent networks as a hash function. So yeah, Jim, what do you think?
So you do the approach similar to the I forgot, kind of sliding window.
Oh, totally. The sliding window. Yeah. So yeah, taking a convolutional approach, right? Because in convolutional networks, your input size or your output size is dependent on your input size. Yeah, that's a great idea. Okay, well, I like these ideas. Let's see how recurrent networks work. So in the past, we've been doing one-to-one. So you have a fixed input size and a fixed output size. With recurrent neural networks, what we're going to do is we're going to have a single neural network unit that we reuse multiple times. And so you can use that for several different tasks. You can have a one-to-many prediction problem. An example of this might be if we had an image and we wanted to capture that image with a sentence. Here is a many-to-one prediction problem, so we can also use them to condense variable length input into one output. So you could think of this as image synthesis, where you have a caption as input and you want to predict an image. You can also do many to many. This is so an example of this would be translation. So you want to translate a sentence from English to Spanish. Sometimes those sentences are not guaranteed to be the same length as each other. There's not necessarily going to be a one-to-one correspondence between words, because sometimes words get combined together and things like that. So yeah, an example of many to many would be translation. And then this is another variation of many to many, but in this case, each input corresponds to a certain output. And so an example of this could be object detection in a video. where for each frame of a video, you want to identify what objects exist in that video and where they are in the frame. Oh, there we go. So another example of many one would be sentiment classification. You want to predict whether an Amazon review is positive or negative. Yeah. So this is an example of the frame classification. So yeah, we're trying to identify street numbers from video of like Google Street View. So how does it work? What does the architecture look like? Well, the way that we do this is we take an input X, pass it into a recurrent neural network, and then feed the output of that recurrent neural network back into itself and just reuse the weights. So this diagram that on the right diagrams the connections between X and R and the RNN, which is that first arrow in the left side. And then we feed all of the outputs back into the RNN. And so we could have drawn another layer of green nodes above the current green nodes and connected all of them via arrows. In this case, but because they are the same green nodes, we're just drawing arrows wrapping around to connect them to themselves, like self loops. Yeah, question?
Just the arrow that's each one's connected to itself, not the right one.
Well, yeah, so let me go a little further. So the rightmost node is connected to all the other nodes. The middle node is connected to all the other nodes, and the leftmost node is connected to all the other nodes. So all of the nodes connect to all of the other nodes at the next layer of the recurrent neural network. And so if I had time, I would redo this diagram because that's just not pretty, and I think it'd be a lot more apparent if we just had another layer of green nodes on top. But that's what we have to work with. So that's the RNN portion. But usually we also want to have some sort of output that we're predicting. And so we're also going to take the outputs of the RNN and have another weight layer represented by this top arrow that predicts a vector Y. And so this is what an RNN looks like in math. So the RNN will take as input a previous state vector, which we will call H, the current input vector, which we call XT, and will apply some parameterized function to it, which we will parameterize by W. And that will produce an output vector H sub T. So this is an example of what that might look like. So we're going to define this F sub W function. And we'll do that by saying, okay, we will have a weight matrix that transforms our input X, and another weight matrix that transforms the previous state, and then we will sum those vectors together. And then we apply nonlinearity, and that will give us our next state vector, H sub T. And then we will also define a third weight matrix, WHY, which maps from the current vector sub T to the current prediction Y. And that's about it. Any questions on the math or the connections or how we lay out this recurrent neural network? Yeah, question.
So does the learn
Good question. So the question is whether there are learned weights from where you connect to yourself. And the answer is those are this WHH. If you think about it, we have this H sub T minus 1 is the output of the previous step of the RNN. and then we apply a weight matrix to it and digest it as part of the current layer of environment. Does that make sense? Yeah, Drake.
Yeah.
Great question. So the question is whether we always add the transformed x and the transformed ht minus 1, or could we also concatenate them? It actually turns out, and you can Google this, that concatenation and addition are very similar operations in neural networks. One of them is a special case of the other. I'm trying to remember which it is. But if you Google it, there's a Stack Overflow question that talks about the difference between addition and concatenation. But the short answer is that they are very, very similar to each other. Good question. Yeah, Grant. How many times do you recur? Good question. So it depends on what problem you're doing. So if you're doing a one-to-many, so I think it might help to have some concrete examples. So let's make sure we answer that question once we get to some actual examples. Don't let me forget it. Okay, yeah, so here's an example, and I think we can do it here. So this is going to be a problem where we are training an RNN to predict the next character in a sequence. So our vocabulary is the letters H, E, L, and O, and we are training it to predict the next letter in that sequence. So if it takes as input an H, what do we want it to predict? An E. If it takes as input an HE, we want it to predict F, L, etc. So yeah, to do this, first we are going to encode each of our letters with what's called a one-hot encoding, or a one-hot vector. The way that we do that is we assign each letter in the vocabulary a different position in a vector of fixed length. So we have 4 letters in our vocabulary. So each letter will each letter corresponds to an entry here. So H is the 0th entry, E is the 1st entry, L is the 2nd entry, etc. So then we will pass each of those inputs through WXH, which is represented by this red arrow right here, and it will give us H sub T. H sub T will be passed through WHH and summed with the output of the next token to get to get H2. And so on. You can see how it maps out. In this case, but Grant asked the question, how do we know how long to go for? And the answer is that it differs during training and inference. So at training time, we know exactly how long our inputs and outputs are, right? And so we just go as long as we have data, right? So if we're training to predict the next letter of hello, then we will do H to predict E to predict L to predict L, then L to predict O. If we were doing text generation to say, I don't know, write an essay, we would probably want to know how to end it at some point. And to do that, what we do is we include an end token, a special token in our vocabulary representing like this is the end of the sequence. So during training time, we would also have as input O, and the expected output would be end token. Does that make sense? And then, so once our network is trained to predict the end token at the end of the sequence, then during inference at test time, we can generate tokens until we generate the end token, and then we're done. Does that answer your question?
Yeah.
Okay. Yes, yes. Generally, recurrent networks are used for data that does not have a fixed length.
So
Yeah.
each of these green hidden layers, it's actually the same hidden layer. You're just
Yes,
taking the
each of
previous
these-
time step.
Well, so I want to make sure we use the terminology correctly. So I would actually call these green boxes hidden states. These are not weights. These are activations. Okay, the green arrows and the red arrows are weights. And yes, each of these green arrows is the same weight, and each of these red arrows is the same weight. Does that answer your question?
Yep.
Okay. Olivia.
So would it be like a one, or would it be like? Do it.
Yeah, so we should write out the rest of this. So yeah, this is a many to many, and specifically the case of many to many where each input has exactly one output.
Yep.
Yeah, question. Do the time steps for time series data have to be the same? It probably depends on what type of time series data it is. It kind of depends on whether you care, probably. So if your prediction problem doesn't depend on the interval of it, probably not. It does, then it probably does. But there are probably ways that you can encode the length of the interval as part of your input for the RNN as well. You know what I mean? So you could like add some other vector here representing like the spacing between this data point and the previous data point. And that would be a way of incorporating that temporality. Yeah. So, oh yeah, where do you get your first hidden state? Great question. You can randomly initialize it. You can initialize it to 0. There are a couple of things that people do. Yeah. It's not a super satisfying answer because it's like, it seems like you're, it seems like what your predictions would depend on that, and it's true. But if you in practice, if you have the same kind of input at train time compared to test time, it can learn to discard that information, and you end up working out all right. Yeah. Is the state something we are learning? I mean, it's an activation. So we are learning the weights, like the weights of the red and green arrows are updated by gradient descent. The numbers of these hidden states are dependent on those updated weights, but they are not the hidden states, the green boxes are not being updated by gradient descent. Does that answer your question? Yeah. Oh, and we're also updating the blue arrows by gradient descent. That's our WHY. All right, so what happens when we create one of these things? So this is, we're going to train an RNN on a character level RNN on Shakespeare. So at the beginning, we get what looks like to be fairly common English letters, but no real coherence to them. Then we start to get things that start to look like words. And then we actually start to get real words and other things that are not real words, but kind of sound like they could be. Hath fair fall on such that the hall for Prince Belzonski's that me of her early and beds to Harwood driving were to it below. You know, it sounds kind of Shakespearean, maybe. Yeah. So this is exactly the architecture that we were looking at, trained on Shakespeare text. What was that?
How does it get? That's not here.
Oh, so great question. So you're asking a question about training versus inference, and that is exactly what you just said is exactly right. So the question is, okay, we train a network on Shakespeare, or apparently Travis thinks this is War and Peace. And once we have a trained network, what do we feed back in to predict the next token? So if we feed in the start token and it spits out A, what do we do? Well, we feed back in A, and it predicts F. And then we feed in A and F, and then it predicts T. So we are using the predictions of the neural network as inputs to predict the next token. Okay. Yeah. Yeah, so yeah, totally. Yeah, so the question is, well, can you increase the length of the prompt to help improve it? And the answer is absolutely. And there's actually an entire subfield of deep learning research right now called prompt engineering, of like, how can you provide a prompt to what we would call this a language model. How can you provide a prompt to get the language model to say a certain thing? And it turns out there are some pretty creative things that you can do. So for example, if you prompt it with an example of like a multiple choice question and how to answer a multiple choice question, and then prompt it with a multiple choice question and several possible solutions, the network can actually predict the answers multiple choice questions. And often, because it's trained on text like Wikipedia, often those answers to those multiple choice questions will be factually correct. And so you can, you have this kind of crazy immersive behavior of where these language models learn factual relationships about the real world. And so that's kind of probably more of an answer than you're looking for to your question about prompts. But yeah, prompt engineering is pretty fascinating. Yeah, Jared. Yeah.
That case, we're from, and then it's giving us out of probably like a word at a time. We keep inputting that original from the word.
Correct. Yeah. Yeah. So whenever you're using an RNN during inference, you provide the entire context at each prediction step. Yeah. Yeah. Go ahead. Well, so the example we looked at provided the entire context. Yeah. So yeah, during training, you always provide the entire context leading up to what you want to predict. So that's yeah. Question. Can you speak up? What are some of the limitations? Great questions. We will get to one in a second. One of them is memory. So you can imagine it, you have an extremely long sequence. In order to be able to use context from the beginning of that sequence, when you're predicting, say, the 2000th word, you need to have information from that first word flow through 2000 iterations of applying WHH in order to predict the last word. And so memory is a really difficult thing for recurrent neural networks. Okay, these are just more fun examples. This is training data from Shakespeare. People have also trained these on LaTeX source code for example, mathematics papers or mathematics textbooks. And this is the result. So we get things that kind of look like math. For the sum from n equals 1 to n, where L sub n equals 0, hence we can find a closed subset, H and H. And any sets F on X. U is a closed inversion. Total nonsense, but it kind of looks right. And I'm pretty sure that people have like actually submitted papers like these just for fun to journals and actually gotten it, kind of used it to expose some of these predatory journals that will accept anything. Yeah, even learning LaTeX syntax for flow diagrams. So yeah, like, and we kind of laugh at these because they're kind of nonsensical, but you think like, what if these things were actually really good? Like actually learn, like I gave you that example of multiple choice question answering and real world knowledge. Like, what if we could train a network on a bunch of papers on the Riemann hypothesis and then see what happens and then see what it spits out? You know, like people are thinking hard about these things. And in my opinion, it's not outside the realm of possibility that we're going to start to see a many new scientific discoveries based on language models trained on scientific papers. Yeah, Matthew.
So GPT-3, they were really going into this, and they got it to the point where it could do high school math problems for like calculus.
Yeah, so that's a good example, and you know it's only up from here. So even if you think you're safe by going into this STEM degree, you might not be. Just kidding. What's your That's a very insightful question. The question is, you know, you talk about RNNs being able to solve these problems that are outside the realm of what we know, but can RNNs be expected to extrapolate beyond their training data or just interpolate what they've already seen? And the answer is, I don't know. Yeah, the question that you asked of whether neural networks can extrapolate versus like are they just interpolating is one that is an open question, and in the field of computer science and AI. So if you're interested in it, do a final comment. Okay, just a couple more examples. Training on the Linux kernel. And we get code that actually compiles. So manages to be syntactically correct at the very least. And also has managed to memorize very accurately the GNU GPL. So yeah, and this stuff is actually a couple of years old. I don't know if you've heard of like Codagen models or OpenAI Codex. Language models trained on code have gotten really, really good and have been shown to like increase programmer productivity by like 2 or 3 times. So, and they're only getting better. So again, you think you're safe by being a computer scientist, watch out. I mean, you know, no one can really tell the future, but it's definitely better to be aware of these things and think about how you can using them in your career and building these kinds of tools. Yeah. And I think we'll end there.